Welcome to MHF4U1 Advanced Functions. This is a Rational Functions chapter. In this lesson number 2, we're going to explore the quotients of a polynomial functions, meaning that we're going to explore some of the graphs that are created by dividing a polynomial function. First, let's take a look at the rational functions. A rational functions is in a form of f at x, px over qx. So you will have a polynomial expressions or a constant in the numerator and in the denominator. Okay. Now, the domain of any type of rational function is always defined by looking at the denominator, making sure that it does not equal to 0. If it does, then if you have a denominator a 0, that means it doesn't exist, okay? Inadmissible. So question number 1. So find the domain of each rational function. So let's see. For the first one, you always want to double check before you let the denominator equal to 0 to see if you could factor the numerator and denominator and to see if you can cancel out. But unfortunately for letter A, you can't factor. So we say x minus 1 cannot be 0. X cannot be equal to 1. So the domain, you could put it this way, is that x can be any real number such that x cannot be equal to 1. Okay, that will be your domain. Next, letter B. So if for the denominator, we let it cannot equal to 0. Okay, so we want to solve for x. So in this case, I could factor a common factor of x, so 6x squared plus x minus 2 cannot equal to 0. Okay, and then so we know for this one, x cannot equal to 0. And now if you factor this out, it's going to be x, it's going to be 2x minus 1, and then 3x plus 2. Okay, so for that, this one is that x cannot be equal to 1 over 2. And for this one, x cannot be equal to negative 2 over 3. So for domain, you could state that x can be any real number such that x cannot be negative 2 over 3, 0, and 1 over 2. Okay. Next, so wholes. A rational function, if you're given a rational function, there may be a whole at x equals a if when a is plugged into the numerator and it gives you 0, and the denominator it gives you 0. So another way to simply remember is that if you could factor and cancel out the numerator and denominator, it's going to be a whole. Okay, so let's show you what I mean by that. So let's say we are given f at x, x squared over x. So first thing is simplify as much as you can. So x squared divided by x is going to be x is equal to x. And we know we have to let x cannot be equal to denominator. But because we canceled it, right? So that this means there is a whole at x equals 0 because you cancel the numerator and the denominator because that will equal 0 at both ends. Okay, so therefore we can draw the grid. Let's see. And so you'll be drawing a final graph that is the simplified version. So it's going to be a linear graph, except that it's not going to include 0. So there is a whole at x equals 0. So whole, I'm just going to write it for you, 0, 0. And it's going to be a perfect linear line. So that is going to be y is equal to f at x. So that is my function of this one. Okay. Next, so we have x squared minus 4 in the numerator and x plus 2. So again, it is a rational function. First thing, as always, is you notice that x cannot be, the denominator x cannot be equal to negative 2. But we want to simplify it. So x minus 2, factor the numerator, x plus 2, and then x plus 2. So as you can see, x plus 2 and x plus 2 cancels out. So what does that mean? There is a whole at x is equal to negative 2 as soon as you cancel out. So my f at x is going to be x minus 2, where x cannot be equal to negative 2. Okay, so when you're graphing the rational expression, you're always graphing the simplified version. So again, so let's graph this. So I'm going to draw the grid over here. Okay, so this is x, and this is y. And let me use a different color. So we are drawing a linear function. So we have a y-intercept at negative 2, but it's a whole. Okay, so at negative 2, my y value, negative 2, is going to be this one. Okay, and so that's my y-intercept. And at negative 2, I'm going to plug it in. Negative 2 is going to be negative 4. So that's negative 4. So there is a hole. And then it's going to be a straight line passing 2, okay, and going this way. Okay. So this is my f at x at x minus 2, where x cannot be equal to negative 2 because you canceled it out. Okay. Now, next concept, you can find the zeros of a rational expression if you let the numerator equal to 0 and the denominator cannot equal to 0. So that's when you know that you have x-intercepts. Let's try this. So find the zeros of the following functions. So it looks like we're given x minus 1, x squared. So we can definitely factor this, x minus 1, which is a difference of square. So you'll notice that these two cancel out. So that means we have a whole at 1. So f at x is going to be 1 over x plus 1. And we know x cannot be equal to the denominator, both of them. Before you cancel out, it's going to be plus or minus 1. So for the numerator is just 1. There's no variable. So therefore, if it's just a constant in the numerator, there are no x-intercepts. There are no zeros. Now let's try the next one. So we have x squared minus 1. So this one, I could factor the numerator. And we cancel that. So it looks like we have a whole at negative 1. So my simplified equation is going to be x minus 1. We know that x cannot be equal to negative 1, which is a whole. And the 0 is, I'm going to let the numerator equal to 0. So 0 equals x minus 1. So that means x is equal to 1. This is my 0. Okay. And there is a whole at negative 1. So if I want to be specific, I can plug in negative 1 into the equation, which is negative 1 minus 1 is negative 2. Okay, so that is where I have a whole. Okay. Next, so let's figure out the vertical asymptote. A simple way to find a vertical asymptote is you always represent it as x is equal to a constant number. And it's a line that a graph will never touch but approach. And how do you find it? That the numerator, it cannot equal to 0, and the denominator, it actually equals to 0. So whatever the denominator can equal to 0, that is going to be a vertical asymptote. And I put a note here that vertical asymptote is going to split the graph in branches. So what I mean by that is we are going to explore the end behavior around the asymptote. So the left side and the right side of the asymptote. So example 4, so find the equation of a vertical asymptote. So again, there's nothing that we can factor, so we let the denominator equal to 0. So x squared plus 1 equals 0. But unfortunately, x squared equals -1. You cannot do square root of -1. So therefore, there are no solution because it's impossible. So the vertical asymptote, there are none. Okay. Next, letter B. So we're going to factor the denominator. So x plus 3. So before you do anything, always simplify as much as possible by factoring. So it's going to be x plus 3 and x minus 2. So again, you notice that it cancels out. So there is a hole. So f at x, the simplified version, is going to be 1 over x minus 2. And we know that for domain, x cannot be equal to -3 and 2. So for vertical asymptote, you have to look at the simplified version, not the original factored form. So vertical asymptote is going to be x is equal to 2. And there is a hole at -3 because we canceled out x plus 3, -3. And I'm going to plug in -3 into the equation. It's going to be -1 over 5. And that's how you find a vertical asymptote. So you may be wondering, what about a horizontal asymptote? So horizontal asymptote can be represented using y is equal to a constant number. Okay. Now, so I represented a rational functions like this, okay, meaning that there are 3 scenarios that I want you to consider. So scenario number 1, if the degree of the numerator and denominator is same, that means the horizontal asymptote is going to be equal to the coefficient of the degree. Okay. So for example, let's say we have y is equal to 3x squared plus 1 and then 5x squared. That means because the degree is the same, the horizontal asymptote is going to be y is equal to 3 over 5 because you're looking at the degree of the coefficient. So the coefficient of the degree. Next scenario, if the degree of the numerator is less than the degree of the denominator, as we saw in the previous lesson, the horizontal asymptote is always going to be 0. But on the other hand, if the degree of the numerator is greater than the denominator, then there is no horizontal asymptote. To expand on further, if the degree, the p of x, is greater than q of x by 1 degree, okay, then we are going to have something called a oblique asymptote. So oblique asymptotes only exist if there are no horizontal, if there is no horizontal asymptote. You cannot have both. It's one or the other. So therefore, how do you find the oblique asymptote? all you need to do is do either a synthetic or long division of P of x divided by Q of x. So the higher degree goes in the division sign, it's a dividend, and the lower degree, which is Q of x, the denominator, is going to be a divisor. And whenever you divide, that quotient is going to be the oblique asymptote. Okay, so we don't care about the remainder. Whatever remainder you get, you just ignore that. Okay, so let's do a practice. So find the equation of the horizontal asymptote if it exists. So first, there's nothing that we can cancel out by factoring. And you notice that the degree is in the numerator is bigger by 1. So that means we don't have no horizontal asymptote. Instead, we have a oblique asymptote because the degree is greater by 1. So how do I do that? Well, let's do a synthetic division. So 2x squared, and then 0, degree of 1, and then 3. So I'm filling it in. And the divisor is going to be negative 1. So let's divide. 2 comes down, negative 2, you add negative 2, 2, 5. So that is my remainder, which we don't look at. So my quotient is going to be 2x, 1 degree less, minus 2. That is going to be my oblique asymptote. Oblique asymptote is always going to be a linear line with a degree of 1. Okay. It makes sense because the numerator is bigger by 1 degree for the denominator. Next, so notice how the degree for the numerator is 2 and the degree for the denominator is 3. So because the denominator degree is bigger, we have a horizontal asymptote. Y is equal to 0 because the denominator is bigger by the numerator. Okay, always. Now next, so sketch the graph of the following function. Okay, so we're doing everything from scratch. So first thing, factor as much as you can. X minus 1, x minus 1, x plus 1, which is a difference of square. And you will notice that these two cancel out. So that means there is a hole at 1, and then f at x is equal to 1 over x plus 1. And we know that domain is that x cannot be equal to plus or minus 1. So I'm going to plug in 1 into the equation. It's going to be 1 over 2. So there's a hole and the domain. Now let's see. So we do have a vertical asymptote at x is equal to negative 1. And we do have a horizontal asymptote. So for horizontal asymptote, the degree in the denominator is bigger. So that means y is equal to 0. And to find the zeros, well, you let the numerator equal to 0. But for numerator is just 1. So that means there are no x-intercept. Okay, so it seems like we have all the information. Why don't we find the y-intercept? So we can find the y-intercept by letting x equal 0. So I'm going to plug in x equals 0. It's going to be 1 over 1, which is 1. Okay, so we have all the information. So let's draw the grid. Okay. So let's identify the key points. So it seems like we have a y-intercept at 1. And then x equals negative 1. And at 1. So I'm going to just label all the key points. Okay, so using a different color, let's try blue. So first thing, so we have a hole at 1, 0, 1. So I'm going to draw a hole over here. Here's a hole. Okay. Next, we have a vertical asymptote at x equals -1. Okay. And we have a horizontal asymptote at y is equal to 0. So right on the x-axis. Okay. So there are no zeros, so we don't care. And we have a y-intercept at 1. So it looks like this one. Okay. So you may be wondering, how do I go about drawing this? So first thing is you want to make a interval chart using the denominator. So it looks like we have a denominator at the zeros is -1 and 1. So we are going to do a sign chart again, and we're going to plug it in. So let's plug in a number that is smaller than -1 into the equation. So let's see, -2. So -2 into x, the sign is going to be -2 plus 1 is negative, so sign is going to be negative. Okay. Now let's plug in between -1 and 0. So let's plug in 0 into my simplified equation. Okay. So then 0, so 1 divided by 1, it's going to be positive. And let's plug in a number that's greater than 1. Let's say 2. So 2 into my simplified equation, it's going to be positive. So what does that tell me? So anything before the -1, it's going to be below the x-axis. So that means it's going to be this way, not touching the asymptote. And anything in between -1 and 1, it's going to be positive. Okay, so it's above the x-axis, we know that. So it looks like this, and connecting. And then anything after 1, it's still going to be positive, meaning above the x-axis. So it's going to follow the asymptote. Okay.